current law. This is the Kirchoff's current law, where the law of conservation of charges are holds good, and this is applicable only for the junctions or the nodal point. Junction means two or more number of conductors where they are joined together. That point of intersection is called by the name junction. Yeah. Here the incoming currents, meaning the currents which are flowing towards the junction must be taken as positive. The currents flowing away from the junction must be taken as negative. So in this case here now, here it is, I1 is the junction, towards that one it is passing here, I will take it as positive, and the I2 is current, again it is passing towards the junction here now, therefore it is taken as positive here. And this is I3, again it is positive, and I4 it is going away here now, minus I4, it is equal to 0. Therefore, the algebraic summation of all the currents at the junction point is equal to 0. If you are removing this and if you are shifting towards this one, this is the sum of all the incoming currents is equal to the sum of all the outgoing currents. Also we can write. Here, similarly, I can write here. I1 is the current flowing towards the junction here. Therefore, I1 is positive. I2 is flowing away from the junction, minus I2. This is flowing towards the junction, plus I3 here. And this is flowing away from the junction, minus I4. This is flowing towards the junction, plus I5. That value is equal to 0 at the junction point. The sum of all the currents, the algebraic summation of all the currents. I am using the word algebraic because current is a scalar quantity. It cannot be a vector quantity unless there is a current density factor. So current density I have not chosen here. I have chosen only the current. The algebraic summation of all the currents at the junction point, it is equal to 0. Otherwise, I can write here whatever the negative sign is there, I can shift it to the other side of the equation. Sum of all the incoming currents is equal to sum of all the outgoing currents. This is about the first law, Kirchoff's first law. Otherwise, Kirchoff's current law. Coming to the Kirchoff's voltage law, where the law of conservation of energy is holds good, and this is applicable only for a mesh. Mesh means it is said to be a closed path where the circuit elements are there, and it is a closed path where the current is flowing. So if there is a closed path, if it is present, then only the current will pass through. That is the meaning. So this is a mesh here. In this mesh here, there are so many currents that I have written here. In different directions, the current you can give it here, whichever that you want. And here, whichever the currents are flowing in the clockwise direction, that I will take it as positive, as I conventionally that I can say. The currents which are flowing in the anti-clockwise direction, I will take it as negative. So just I will going to consider like this now. I1 is positive here, I3 is negative, and here there is no current, and I2 is said to be the negative. So just to take the product of current and resistance according to your Ohm's law, current into resistance, here there is no current, no resistance here now, no problem. Even though the current is present, even if I am writing a current here, since the resistance is equal to 0 here, so resistance multiplied by the current is equal to 0. Therefore, even though the current is present like this, or current is not present here, no problem. So I4, even if I am introducing here, into resistance is equal to 0 according to Ohm's law. So coming to this concept here, this is A, B, C, D, A. It is a mesh, closed mesh now. Started with A and ends with A. Now I will write here. This is positive, I1, R1, it is a positive here because current is flowing like this. I3 is negative, minus I3 and R2, minus I3 into R2, product of this current. And don't forget, the current whichever is flows through the particular resistance and that current only, we have to take the product. You cannot take this current and this resistance. In this resistance, this is the current flows through, there it is, therefore this product only we have to take. This product only we have to take. Again, we are supposed to take the algebraic summation. So here, voltage is also a scalar quantity. Voltage is equal to current into resistance. Therefore, I have chosen the product of IR here now. The algebraic summation of all the IR products that I will take it up here. So up to here it is finished. Now I will go for this I4 into 0 here. This is minus I2 into R. This is algebraic summation of all the IR products, that is equal to the algebraic summation of all the EMF. Unfortunately or fortunately, here only one battery is there, one cell is there. Easy for us to write. This is only one cell that is having E. Just I will move it like this now. Since we have reached to the positive terminal here, I will write minus E. If I am reaching negative sign here now, or negative terminal here, I will write positive. Otherwise, the current whatever it is flowing, always from positive to negative. I will show it here. Positive to negative current is flowing. If you are considering only the EMF, forget about all these things. Positive to negative like this. This is opposite to this direction. You can observe that it is opposite to this direction. Therefore, this is negative. Otherwise, blindly, just you move it like this. First, if you reaches to the positive end of a cell or a battery, you write the opposite sign here and write the EMF. So this is the way that we are supposed to write. And coming to the second example, under Kirchoff's second law here, I can write again ABCD. A is said to be a mesh. Here I will start with this. Okay, I2, R2, and here it is minus I3, and this is R4. Whatever the resistance is there, you just multiply with that one. Here it is plus I4, R3, and here it is minus I1, R1. That is equal to here. That is equal to EMF that I had to write. I will move it from here to here. Negative sign that, negative terminal that I am touching first here. Therefore, I will write that is equal to. I will write it here is equal to. Here it is positive, that is E2, and here this is positive E1, and this is positive E2. So sum of all the IR products is equal to sum of all the EMFs. It is applicable only for a mesh. It is applicable for a mesh. Similarly, let us apply here. If I am applying here now, this is a mesh. ABCA. ABCA is a mesh. Let us apply from one end. We have to start here. I will start from here. This is I1. This is R3. Positive. This is minus I2. And this is R2. Even though that I have written R2 here and I2 here now, I2 is passing like this only. So therefore this current and this resistance only we have to multiply. And coming to here now, this is like this plus I3 R1, that is equal to here. I will start from here again. Positive terminal I am touching here. Therefore it is said to be the minus E2, and here it is said to be the plus E1, and here it is said to be the minus E2. Are you following this? First idea. Is it clear? Next concept. What is that next idea here? The next idea for this example number 4. For this example number 4 here now, ABCDA is the mesh here. This is the convention direction that I will choose. Means clockwise currents must be taken as positive, anti-clockwise direction must be taken as negative. EMF is also like. For this mesh, ABCDA mesh here, I will start from here. I2 R3 positive, minus I1 R2. Okay, coming to here, minus or plus? Minus I4 R1, and coming here, plus I3 R4 is equal to here, EMF that I have to write. EMF here it is positive, plus E2, minus E3, and this is minus E2. Yeah, only 3 EMFs are there, but I have written 3 EMFs. Okay, coming to this here. This is a mesh here now, A, B, D, A. This is a mesh. And these two are most important for us here, for the next derivation. Okay, for the Wheatstone network, Wheatstone bridge, or balanced condition of Wheatstone bridge, these two particular circuit diagrams that we are supposed to use it. Now, how we are supposed to use it here now. And all these things, it is helpful for your problem sections and somewhere else. Now, let us focusing on this. Here, there is no EMF, there is no cell, there is no battery here. Since there is no cell or there is no battery here, the EMF must be taken as 0, nothing else. So, I will start from here. This is plus I1 and into P. P is the resistance here. I1 into P. P is the resistance. Here, IG is the current. Here Ig is the current, plus Ig, carefully see that, plus Ig. G is the resistance here, multiplied by G. And goes to here, minus I2 I suppose to write, minus I2 into this resistance, that is R, that value is equal to 0. And third idea here, no? Similarly, this here. Okay, if the current is passing in the opposite direction, that I supposed to take it as minus. So you see here, in this circuit, current is flowing like this, Ig. But here, the same current, Ig is coming like this, Ig is coming current like this. But here it is taken, it has to be taken as positive. What will happen? You check it out here. Okay, for this mesh, BCDB mesh, I will start from here. This is the current. Whatever the current is flowing is I1 minus Ig, I have chosen here. I1 minus Ig bracket. That is a total I1 minus Ig current is flowing through Q here into Q. Okay, I1 minus Ig into Q, I1 minus Ig into Q goes like this. This is the current flows through here. This is a minus current here, not negative current. Therefore, it is minus I2 plus Ig. You have to put the bracket, don't forget, because this is the current, but it is negative, into S. Into S. Next, it is coming here now. This is minus Ig into G. Minus Ig into G is equal to 0. You see that here it is plus Ig, but here it is minus. It is same whatever the current direction it is present here also and here also. But here in this particular mesh it is acting as negative. For this mesh it is acting as positive. Clear? Followed all this concept, you see that.